All right, today I'm going to do a brief introduction into the solution making process, and a little bit of solution stoichiometry. And what I'm going to start with here, the sheet of paper is going to represent a 1 liter container, and in this case the white and the green Lego, that's going to be initially hydrogen chloride gas, but when I bubble that into this container, it's going to ionize. I'm going to get H plus ions and the Cl minus ions. So if I place 1 mole of that into my 1 liter container, I get 1 mole of H plus and 1 mole of Cl minus ions. And I'm going to assume as I do these experiments today that adding the extra molecules doesn't affect the volume. Now, as you'll learn with some titration calculations that we'll get into later on, that as we add these, we are actually changing the volumes. But for today, for this brief intro, assuming no volume change. So here I've got 1 mole of HCl in a 1 liter container. So if I want to calculate the molarity of this solution, molarity equals moles of HCl, which is 1, per liter volume, which is 1 liter, 1 mole in 1 liter, I get what's called a 1 molar solution. Now, if I take that same mole and I put it in a ½ liter container, now I've still got 1 mole, but it's in a 0.5 liter container, so that ends up being twice as concentrated. That's a 2 molar solution. Right, so the next one I'm going to do, I'm going to go back to a 1 liter container size, and I'm just going to go through these kind of step by step. So here's my 1 mole per liter, and if I add another one, now I get 2 moles. Again, this is HCl, and it's going to ionize, and then I'm going to go ahead and go 1 more, so now I've got a solution that has 3 moles of HCl per liter, so that's a 3 molar solution. Now, there is a point where we get this completely saturated. We can't add any more, and that's called a concentrated solution. In the case of hydrochloric acid, that would be 12 molar at room temperature. It's considered to be a concentrated solution. We can't get any more under those conditions. We can't have any higher concentration. All right, so now changing this from just basic solution process to a little bit of solution stoichiometry. So what I'm going to do in this 1 liter container, I'm going to introduce a sodium hydroxide, and the yellow is going to represent the sodium, the blue is going to represent the hydroxide. Now, sodium hydroxide, like HCl, although HCl is made from a gas when we do this, sodium hydroxide typically from a solid. I place this in here, and it's going to ionize as well, the sodium ions into the chloride ions. Now, when I do that, I get 1 mole of sodium ions and hydroxide ions. I get 1 mole of sodium, 1 mole of hydroxide. First thing probably that we should note is we should write the reaction, what happens between HCl and NaOH. And when we write this, we're going to write NaCl plus HOH. Now, on the other hand, if we look at this from a standpoint of an ionic equation, this we've already learned is aqueous. It ionizes. This is aqueous. This is also an aqueous salt. Water, of course, is a liquid in that. So the net ionic equation, really, really important to note, H plus OH minus makes HOH. And that's what we see when we do a strong acid, strong base titration reaction. So when I introduce the sodium hydroxide, a common misconception is that the sodium and the chlorine make this sodium chloride. But the reality is the sodium and the chlorine that's introduced, sodium ions and chloride ions introduced, those are spectator ions, so they don't actually form that unless we were to get this to the point of being neutral and evaporate it. Otherwise, they're going to stay in ion form. On the other hand, the hydrogen and hydroxide, those actually form a water molecule. So now there's 1 less H plus than what we had before. There's still the same 3 chlorides that we started with, and now we've also got this sodium ion in here as well. So if I introduce another sodium hydroxide, it's going to ionize. Again, same reaction. Again, these two aren't going to go ahead and combine together because they stay in aqueous form, but the H plus and the OH minus gives us another water at that point. As I introduce the third sodium hydroxide, this is where I reach the equivalence point in my titration, where my mole ratio is 1 to 1. And now at this point we've got our neutral solution, because all the H plus has been bound up to make water with all of the hydroxides that we had present as well. We still got the 3 Na pluses, we've still got the 3 Cl minus. Again, those are going to stay in ion form in this solution. If I introduce an additional, if I continue this titration on, this will ionize, and now all of a sudden I have excess hydroxide. So if I were to go through this from a standpoint of what the titration would look like, initially, if I plot the pH as I'm adding greater quantities, I'm going to have excess H+, so the pH is going to be low. Then when I reach that equivalence point, it's going to go up, and then as I go to the excess hydroxide, it's going to level off. And a strong acid, strong base titration, these points here where we have excess acid and excess base, they're only going to change slightly. Now when we get into strong acids and weak bases and strong acids and weak bases and weak acids, we'll see that curve changes a little bit. But for these, it's going to stay pretty low, just very, very slight changes. Then we're going to get a really, really high vertical jump, and then it's going to kind of slowly increase, but fairly level thereafter. This is also why when we're doing these titrations, to find the endpoint, when we actually stop the titration, we normally correlate an endpoint to a balanced equation equivalence point. Endpoint, again, is just when we stop titrating because the indicator has changed. We're normally a drop or two away from the equivalence point, hopefully a drop or two away. Calculation-wise, that drop or two above or below the equivalence point still gives us reasonable results. Because for a strong acid, strong base titration, this is such a vertical type jump, we can normally use a lot of different indicators for titrations such as this. Really anything probably from a indicator that changes around 4 up to something at 10. So bromothymol blue, phenolphthalein, methyl orange, methyl red. You could probably do this titration with any of those among several others also because of that change. All right, so for the final phase of this, I'm going to go back through again the same process that we just did. I'm going to start with my hydrochloric acid, my 3 molar solution. Again, it is 3 molar because there's 3 moles of HCl per my 1 liter container. And I'm assuming that as I add molecules, again, I'm not changing the volume here. So right now this is a 3 molar HCl solution. Now when I introduce my sodium hydroxide, now at this point the concentrations change. Again, I'm not taking into account anything other than a 1 liter volume in this particular example. So at this point, if we were to calculate our concentrations, if we were to call it HCl, there would only be 2 moles per liter. The better way to describe that is there's 2 moles per liter of H+ ions, there's 3 moles per liter of chloride ions, and 1 mole per liter of sodium ions. So as I introduce another, at this point, now the H+ ion concentration drops to 1 mole per liter. We've got 2 moles per liter sodium ions and still the 3 moles per liter of the chloride ions. And another introduction of sodium hydroxide. I get another water form. So now I have no H+, no OH-. That's why at this point this is a neutral titration. We are at a pH of 7, again because it's a strong acid, strong base titration. I've got 3 sodium ions, 3 chloride ions present. If I introduce another sodium hydroxide, now I've got 4 sodium ions, 4 moles of sodium ions per liter, 4 molar sodium ion, 3 molar chloride ions, and a 1 molar hydroxide ion concentration. Later on, we're going to learn that finding that H+ concentration, or later on, as we are here, that OH- concentration, we're going to be able to do some pH calculations with that, and I'll be doing future lectures where I show how to actually take those values and do the calculations to find the pH.